A single semiconductor crystal like silicon or germanium is doped to make one region as a p-type material and an adjacent region as an n-type material. This is done by a special manufacturing process. You cannot simply glue together an n-type material and a p-type material to get this junction. Because the junction is extremely thin, it is of the order of 10 to the power minus 6 meter. Now let's talk of the charge carriers when the junction is formed. Say I light an incense stick at one end of the room, then the incense molecules diffuse into air. In the same way, the electrons have a higher concentration on the n side and the holes have a higher concentration on the p side. So when this junction is formed, the electrons start diffusing from a high concentration region to the low concentration region, and the holes also diffuse from a high concentration region to a low concentration region. Let's just draw this. See, these are the atoms and we'll draw the charges now. On the p side material we have an excess of holes. So these are the holes, and along with each hole you have a negatively charged lattice side. See, at times you tend to get confused with the signs. Now the material is neutral and a hole is positive, so you have positive, negative, a hole which is positive, the lattice side is negative, positive, negative, positive, negative, positive, negative, because you have equal number of positive and negative charges. So we can draw all the holes and the corresponding lattice side atoms in this way. On the n side we'll have an excess of electrons, so you have a negative electron and a corresponding positive lattice side. Again the material is going to be neutral, so one negative and one positive. Now you can see that electrons are majority carriers on the n side and holes are majority carriers on the p side. When the junction is formed due to diffusion, the electrons will move across the junction in this direction. When an electron moves into a hole over here, it occupies this vacancy, and you can see that this vacancy no longer exists, or you can say that the holes disappear. I'll just erase these now. I'll be erasing the electrons from this side and the holes from this side because they have disappeared. You can see in this region close to the junction there are no free electrons over here because they have moved over and occupied the holes over here. There are no holes over here because these have been occupied by electrons. So you can see that in this region close to the junction there are no free charge carriers, there are no mobile charge carriers. You have a layer of negative charges and positive charges over here, but these charges cannot move. They are a part of the lattice itself. If you recall, say this is the doped element. Now this is bound on all sides by covalent bonds. You have silicon atoms present over here on all sides, and let's say this was the dopant atom which was arsenic. So this ion cannot move, so these charges are not able to move. Now this region is called a depletion region because it is depleted of all free charges or mobile charge carriers. So what you see now is a layer of charges which is building up close to the junction. We can show this in this way. On the n side you can see that we have a positive potential, so we can show it as a positive potential, and on the p side we have a negative potential. So this is a negative potential. This is on the n side and this is on the p side. Now when more electrons try to diffuse across the junction, then this layer of negative charges which is present on the p side repel them and oppose further diffusion. So now there is some kind of a barrier, and this prevents further diffusion of electrons to take place. This potential difference which stops further diffusion of electrons and holes across the junction is called a potential barrier. See, the potential barrier is less than 1 volt. It is about 0.7 volts for germanium and 0.3 volts for silicon. So far we've been talking of the diffusion current, so we've been considering the majority carriers. Now let's take a look at the minority carrier. Now you know that at temperatures higher than 0 Kelvin, there will be a few electrons on the p side and a few holes on the n side. These are the thermally generated charge carriers. Now the potential barrier stopped the electrons from crossing over to the other side, but for these electrons over here, these electrons will get accelerated and they will tend to cross over to the other side. So now the electrons and holes that are present are swept across the junction due to the barrier potential that was built up, and they constitute the drift current. So now we can say that the drift current is due to the minority carriers which are present on the p side and the holes which are present on the n side that are swept across the junction by the barrier potential difference. In an isolated p-n junction, the drift current is equal to the diffusion current and the net current is 0. We'll have some fun today. Solve this crossword puzzle to test your understanding. Hope you enjoyed doing that crossword, and here are the answers.